convention just got cut out. That's pretty funny. All right. To recap what I was saying, recently I decided I want my scripting language to be both as fast as possible and as convenient to use as possible. Unfortunately, we have the concept of structures in our language, and not just structures, we have discriminated unions. Discriminated unions don't exist in things like C. Well, technically you can represent them in C, but you can't enforce, easy grammar and stuff like that. Anyways, here, let me just make sure that this is working. Yes, it looks like it is. Okay. Making sure we're not dropping frames. Yep, we're good. Okay. Yeah. So originally I was just going to come up with my own standard convention for how to pass structures. Like, oh, you just always pass a pointer or something like that. And then maybe do something fancy for smaller structures of like, oh, if it's like a one element structure, pass it as if it was just that member or stuff like that. But the thing is, I really want this to be easy to use on every architecture. Like, wouldn't it be so nice if you could call a Brane script function and just pass a structure to a function and it would just work? Luckily, there is actually a standard for how to do that. And that's the C ABI. Unfortunately, the standard is different for every operating system and every architecture. So Linux on different architectures have different calling conventions. x86 Windows and x86 Linux have different calling conventions. Apple on Arch 64 has different conventions than Arch Linux, even though they are both Unix-style operating systems. Nothing agrees on how to pass aggregate types through functions. So I decided we're going to implement them individually for every single platform, every single architecture. Because at the end of the day, how hard can it be, right? It's an absolute nightmare. Anyways, to get on with the stream, I've been working on this for a few days already, and my biggest problem so far with this is that for security reasons and just basically cleanliness of the bytecode, BraneScript doesn't have the concept of a stack. Like, the intermediate representation doesn't have the representation of a stack. So when I have something like discriminated union, which is our case, so let's say we have a discriminated union with a couple different variants. The way that that's stored, when it's not stored in allocated memory, so the heap, is Pirate Software MS Paint tutorial incoming. You want me to switch to, like, what is it? What's the browser-based thing? Which I actually tried out, and it was pretty nice. Excalibur? Yeah, we could do this instead. This is my explanation of the difference between ECS and all this stuff to throw when I was helping him out with that. Okay, there you go. We're not totally Pirate Softwaring it right now. Okay. So, let's say that we have a discriminated union. So it will have a discriminant, so this is like an int here. And then we have, like, different structures representing different, like, values that it could be. When we're working with values not stored in memory, so these are like the values that it can actually work with, we actually treat discriminated unions, enums, as if all of its different variants simultaneously exist at once. So we have SSA values for each one of like the variables in each one of these variants. We have representations of all of those. However, when we pass something to function, there are two different ways that structs generally get three different ways the structs generally get passed. Two or three. I'm gonna say two different ways structs get passed into functions. One way is if the struct is small enough. Generally, on Windows, this will be if it's less than 64 bits. On Linux, however, Linux x86 Linux, you can actually have two 8-byte. You can split a struct into two 8-byte sections. So you can split it up into two ints, basically. So 64 times 228, right? But generally, any structures larger than 128, you allocate a new bit of memory for this on the stack, and then you pass a pointer to that struct into the function. Now, even standards can't even agree on that. In Windows, you use the standard way to pass arguments to pass that pointer to the struct you've allocated on the stack somewhere. But in x86 Linux, or System 5 if you're being specific, you don't actually pass a pointer to the struct. You implicitly put it on the stack in a certain place, and the function, because it's also using the same ABI to read its arguments, knows where on the stack to grab that from, and then just grabs it. So basically, the two different ways that you can pass a structure are, one, you pass it as arguments to the function directly if it fits in registers, or you pass it on the stack. And I'm just going to say pass on the stack. I'm not going to say pass a pointer to it, because that's a different way of... There's just different standards for how you pass it on the stack. And then, of course, when you return a function, you can either have an implicit function pointer that's like the first argument to a function, and then it's like, oh, I'm supposed to, when I return the function, I actually just take that memory and set that memory to the return value. Or sometimes you can pass a structure back in a register value. But here's the thing. The hardest part out of all of that isn't like keeping track of what does where and when, because like I have three different documents open right now. We have Windows, we have Linux x86, and then we have ARM 64-bit, because we have to get this working on a Quest, which is a mobile chipset running Arch 64, which is the ARM 64 standard, or AArch 64. So these are so minimum we have to implement these three different function calling conventions. Anyways, the hardest part about all of this is because we represent our types like this as we don't have a stack as a concept in our intermediate representation. And that works fine because we just use single static assignment node variables, basically form a graph of everything, and then we let our JIT compilation backend decide what goes on the stack, what stays in registers, through its like already existing overflow methods. So we just don't worry about the stack at all. The JIT compilation abstracts that for us. However, of course we need stacks sometimes when we need to pass a structure on the stack. And the JIT compilation has a way for us to explicitly tell it to do that. And I've come up with this standard of like how to, in the intermediate representation, represent passing this array of flattened values which represents objects to functions and whatnot. Now, the hardest part about all of this is in the cases of Windows and also x86 Linux. I haven't checked ARM yet. I haven't fully read this document, but in both of these, there are instances where you pack both integers and floats, as well as other types, into single int values. Now, this wouldn't be too hard to do if we had the concept of a stack, because when you bitcast things, it's essentially the same as like writing something to memory and then reading it back as a different type. But we straight up don't have the concept of a stack. What we have is this concept of every single variant of an enum existing simultaneously as values in this graph. And then, like, when we finally JIT compile that, that gets resolved into, like, you know, if we use this int value here, or if we read this int value here, it tells us at runtime which one of these variants the enum actually is, and then at runtime we also only use those values that are treated as if that exists. That's cool and all, but the problem is when we have these two cases here, where you have a structure that can fit into 64 bits, or in the case of Linux, 128 bits. And Linux is even more complicated because they describe an entire algorithm. Where is it here? Yeah. They describe an entire algorithm to classify structures as either an integer value, an SSE value, SSE up, because Linux has in its spec that if you have multiple floats in a row, implicitly you're supposed to, when you have multiple floats, you can pack all of those into a vector register. So for those who aren't familiar, vector registers are on the CPU. Instead of having one float in a register, they can have up to 4, 16, I think it's 16 at the most, but you can have like 518 bytes of float in a single register. And if you've ever heard the term SIMD, that's what those are used for, simultaneous input, multiple data. That's where you can do like a multiplication on a set of 4 floats against another 4 floats at once. That's how that's one of the ways modern computers are like really, really fast, is because they're doing 4 to 8 to 16 multiplication operations in a single instruction. Now, that's cool and all, but it does mean that we have to now implicitly detect if we have 4 floats next to each other in a struct, when we're passing that to when we're passing that into a function, sometimes implicitly, we're going to have to vectorize those floats, which, to be honest, that's not going to be too hard. We just have to know that that exists and everything. Anyways, the hard part that Linux has us do that's harder is that, where is it here? One of these here is, if one of the classes is memory, the whole argument is passed in memory. So that's your implicit on the stack. If x87 up is not preceded by x87, the whole argument is passed in memory. So that's like a failure to vectorize. And then here, if the size of the aggregate exceeds 2 8 bytes and the first 8 byte isn't SSE, or any other 8 byte isn't SSE up, the whole argument is passed in memory. So this here, if I'm reading it correctly, if the size of the aggregate exceeds 2 8 bytes, so we're talking about larger than 2 8 bytes, and then it's not following a SSE and then isn't SSE up, the whole argument is passed in memory. So that's basically if this is larger than 2 8 bytes and we can't put floats into vector registers, then it's too big, pass it implicitly on the stack. That's basically your point, pass the struct as a pointer, but implicitly. But because of this line here, if the aggregate exceeds 2 8 bytes, that means if it's 8 bytes or 2 8 bytes or less, that means you can still pass up to 2 8 bytes as registers. And each one of those 2 8 bytes gets its own, or 64-bit register. Those 2 8 bytes can be classified separately, so we might be passing half of the structure as a float, half of the structure as like a vector argument or a float argument. Basically, it's just a little bit more complicated because I can't just account for the case of structs always getting cast to one register argument. It could be cast as 2 register arguments, which, just makes things a little bit more complicated. So to kind of type this out all out, the things we have to account for are regular arguments, easy. We don't have to worry about which registers to pass stuff in, at what point do we overflow and start passing arguments to this function on the stack. We don't have to worry about that. Crane lift takes care of that. So all we have to care about is specifically how do we pass enums and structs to functions. And because I have a well-defined where is it here? For passing enums to and from functions. Yeah, because we're going to copy Rust reproduce C representation for enums. So basically, our enums will be fully interoperable with Rust enums that have a certain annotation, which will be really cool because you can just natively pass not only structures, but enums to and from Brane script without any casting or overhead or anything once we have this implemented. Basically, that means you have your discriminant value as the first value of the structure, and then you have a union as the second half of the structure, and just use the standard layout rules for both that int and those enums as if they were in a struct. All right. So yeah, that's how we're gonna pass enums. They're just gonna be a different representation of struct using a union type. Yeah. So the only things we have to worry about is casting int plus float, or casting multiple struct values into a single int register. This is the main thing we need to worry about. Now, I'm implementing Windows first because I am still running deprecated Windows 10. So we're going to get Windows working first because Windows is actually the easiest one to implement. Now, just because it's easy, does that mean I like it? No, because you're locked to 4 register arguments total. Even though they allocate 4 integer and 4 float arguments that you can use, and I think you might be able to use maybe vector registers as well as a pointer. No. Yeah, it's only integers or floats. You can pass as arguments to Windows functions, and they're statically allocated by index instead of Linux, where they're like, you can use so many registers to pass function arguments on Linux, like it's crazy. You can use up to 8 integer arguments. I think I think you can use up to 8 float arguments, and they're allocated based on need before you start spilling to the stack. And you can use vector registers to pass. They call it Windows Fast Call. It's fast to implement, not fast to use. That's all I'll say. So yes, even at the level of the way functions work, Linux is better. Like, technically so. Now, because this is simple, I'm sure in the days of, like, handwriting assembly, this was more consistent and less bug-prone. Nobody's hand-rolling assembly except for FFmpeg anymore, so... yeah. But it is the easier one to implement, so it's the one we're going to implement first. Which means, to get this working, we need to account for straight casting both casting struct values into a single int register, and then we also need to account for casting union values from flattened SSA values to single int values. Now, this is the thing that got me to say I need to stream this instead of working on it offline, because we're going to need to write, like, straight up, we're going to have to write branching logic for this, like runtime branching logic to do this. Because, as I said, you need to read this value here to figure out which one of these values to use, and we can't do something simple like just doing some fancy XOR operation on all of these, because, you know, then the values won't be correct. We have to actually do a branch-based store into this integer, or branch-based load from an integer. Let's see. Union values to and from, and then struct values to and from, single int. And then we can worry about how we're going to implement this next. Because of WSL, we'll be able to test this next, because we will be able to test directly on Quest if our Rust code works without having to make an entire Quest application, because we can just ADB run raw command line scripts directly on device if it's plugged into my PC. So I'm not worried about that, but that is what we're going to do last, just make sure Quest is working. So the only thing we need to worry about for now is struct values to and from. You need to be able to account for multiple int registers, and maybe read a little bit more into these specs for how unions should be defined. I'm basically, the way I'm currently treating it is that each union, this is the wrong document. The way that I'm treating unions is that each union variant is treated with the alignment as if it was its own C ABI compliant structure with all the padding and whatnot. It's rather simple, and I think that's probably the way that they want us to handle this. So, talking out loud, the main problem I do need to solve right now, and I'm even procrastinating by giving this explanation because I really don't want to do it, is this casting union values to and from flattened SSA values into single int registers. And Yeah. I do wonder how... Don't worry about it. I do not expect many people to understand basically anything of what I'm doing in this stream. All you need to know is we're at the point where we're reading like specification documents, because even like chatbots get a lot of this wrong. I had a chatbot link me these documents, and I haven't asked it too many questions since. Basically, follow the spec sheets. Yeah, but we're doing Windows first. You need to figure out how to cast union values from flattened register values into int registers. This is the hardest thing, and it's the thing that we have to implement right now, which is fun. So right now what I have is this cast to int function, and also cast from int function. And what I was trying to do is, originally it was struct cast from int and struct cast to int. Is this a Linux assembly code PDF? Not necessarily. It's the specification for procedure call standards. So this is how to do procedure calls in assembly. So that's function calls in assembly for x64, Windows, Arch, ARM64, and then also x86 System 5 function calls, which that's Linux, or most Unix systems. I have not switched to Linux yet. I'm just going to procrastinate for a bit, because, you know, I don't want to. That's a lot of, it's a lot of work. I'll be out of... I will be out of commission for a little bit while I do all of that, because I will actually take the time to, like, set up my own distro and all of that. Well, not distro, but, like, fully customize something and get it working, and, like, you need to get VR working, too, and... And Windows 10 is going to keep working for a while. Okay. So, the thing that I'm annoyed about, to keep procrastinating actually doing anything, is that if I go to my compiler here, you'll see this thing called SSA enum and SSA structure. And these enums and structures have utility functions to create these structures from a set of flattened values. So that's when I have, like, every single register value or SSA value that represents this struct can be unflattened into this struct representation, and then we can also flatten it back out. And that makes them a lot easier to work with, because I actually can map, like, it's more useful for enums, but it makes it really easy to work with the fact that, like, structs can contain other structs. And from, like, a flattened representation, you can't tell, like, which struct is which struct, which values are, like, which variant of what enum. These structures kind of, they solve all of that. They handle all of the flattening, unflattening, all of that stuff. The problem is that this is on the compiler side, and this is on the backend side. So these are entirely different code. None of this code is actually, or none of this code here, none of this file exists on this file, because you're supposed to run the compiler and then you get a binary, and then that binary is what you ship to your actual runtime, and that's where you like run the code and whatnot. Whereas this is the code that is loading that already compiled code. And, you know, this code is supposed to be dumber, easier to write, all of that stuff. But the problem is, because we're trying to abstract this runtime, make it safe, it needs to have concepts of structs and enums again. Meaning, what I should probably do is straight up just copy all of this code over into the backend, which is what I'm going to do eventually, but I'm moping about it. The other thing I wanted to show off was we can actually look at somewhere in here, function load. Yeah, here it is. So in here, if we try to load an enum value, what the compiler does behind the scenes is it loads the index value, or it emits an operation that loads the index value, and then we can use that value to create a jump map. So that's what this does here. It ends the current block and begins a jump map. And that jump map gives us, we give the jump map a bunch of branches that the jump map could jump to, the values that we want to jump to on those jump maps. Basically, this is how you emit a switch statement from the compiler side. And then for every single one of those branches, we then load the IR values that each one of those, we load the values for each one of those branches. So if the variant is the 0th variant, we load that. If this variant is the first index, we then load that. But because this is the compiler side, we just emit the code for loading all of them, and then we store all of those loaded values in this SSA enum. So this SSA enum at any one time actually contains values that may or may not actually exist at that point in a program, because we're assuming that before attempting to access these values, you check the index value. So the values may or may not actually exist, but you know, they exist, you know? And then our JIT compiler does do, uses a control flow graph to figure out if those values will actually exist when you try to use them or not. So you don't have to worry about using a value that doesn't exist when it doesn't exist, or using a value that may or may not exist when it doesn't exist. The annoying thing is, instead of doing this on the compiler side, where I've already written out all the logic to deal with this, now we have to secretly emit one of these in front of every single function that is going to call or return like the values of an enum. And like there's a little bit of like iffiness of when we use those enum values, should it lazily load those SSA values? I don't know. I think that our JIT compiler will do a tiny bit of optimization and moving stuff around to make it so we only load the values when we actually need them. But that's also something that we can figure out at a different time. At the end of the day, this will still be the absolute fastest way to handle all of this. But enough complaining. Enough complaining. Let's actually just straight up copy these over. Because I need structured values. And we're going to have to completely rewrite them, but we can keep the general structure because in this version of it, we are using the intermediate representation, whereas in where we're copying it to, we're going to be using the native value type of crane lift. And then if we use LLVM actually does have concepts of aggregate types, so we might not, if we ever rewrite the LLVM back, like if we ever recode the LLVM backend, we might not need to have our own implementations of SSA struct and SSA enum. We might need to do it for the enums, but we won't have to do it for the structs because LLVM actually does handle all of the C ABI stuff for us, and they do also have their own representation of aggregate types or structures. Anyways, that is now copied. Now we go to Brane backend crane lift, and let's just drop these in here. So instead of our value, this will just be value. Well, actually not value, because these could be nested structures and all of that stuff. So we actually need the concept of, is this value or object, which almost works, but it's not good enough. In fact, I'm going to delete this because it's not what we want. And then we're going to create a new enum, which isn't our value. We're going to say what's a good way to say unflattened? We could just call it structured value. I'm just going to call it S value for now. And S value will consist of value, which is just value. The question is, do I want to store a Brane script type for this? Or only for... I want to keep these as small as possible to keep it as, like, throughput going good. They're going to call this value struct SSA struct or enum. This is going to be an SSA enum. And this S value is what we're going to use Structured values are an abstraction over the flattened representation we use for structs and enums. Useful for easier construction of function arguments. And if we weren't doing fancy enum or fancy not even fancy, but just ABI compliant function stuff, we wouldn't have to make these. So SSA enums. This will just be a value. This will be an S value. Index type. You want to keep this as an IR type, or you want to change this to a not a type, a no. Somewhere in here I have self JIT type. And then that returns whatever crane lifts type is. JIT type. This returns a type. Okay, got it. It is just called a type. Hello, welcome back. I think we won't store the Brane script type for this, but we will store the crane lift type for it. Because we'll have references to the Brane script type stored by SSA struct and SSA enum. So in situations where I do need, actually I don't need it at all. It's only in the cases of enum and structures to be able to recreate their structure and alignment, basically. So def ID, perfect. IR enum ID, all of that looks good. We can keep this exactly as it is. Similarly named S value. Defined where. Okay, so it's just saying that. Got it. This is complaining about these implementations are incorrect. So I think cast to int might become a part of the S value. The other really nice thing I'm seeing about, I've realized, is because of the way that variable alignment works, it actually makes it really easy to impact stuff, because you'll never have one value cross the boundary of two function arguments. Like, you'll never have like half of a float value here and half of a float value here if it's a 64-bit, because 64-bit variables want to be aligned to a 64-bit memory address, meaning that if you have like a 16-bit value in your struct and then a 64-bit value in your struct, like, they'll align themselves, so when you cast them to two different ints, there's no data shared between the two of them. Just thankfully I don't have to deal with reconstructing a value across two different registers. Because that would be something I want to write in higher level code than raw assembly language, which is kind of what I'm doing here. Abstracted assembly language at that. Okay. So we're going to change this to S value. Okay, fields. This won't be value, this will be S value. And because we don't have to deal with user code here, we can refer to fields entirely by index because we're dealing with IR. Goodbye string operations. And then on SSA enum, okay, that's already by index. So we're good. No string operations. So let's go through and let's implement this. So I'm not sure what new slice does. Is this new from slice? I'm just gonna copy over the code for our value. Because our value, we do have all of this. And that from flattened is probably the most important struct here. Hello. So let's replace our value with S value right off the bat. And most of this code will just kind of carry over, won't it? Now, in any of this code, do I do new slice? Nowhere. Oh, okay. What's happening here is this literally is for new slice. Like if I am creating a slice type using a structure, or a slice type is a structure, is represented as one. But we don't have the user to do that. So that's what I was doing there. That's compiler only code. We can delete all of that. Slice type just creates a struct that is of a type slice. Checks if a struct represents a slice. We don't need that because all that abstraction has already been done by the intermediate implementation. This is just getting the definition. You don't need to worry about that either, because I've just been doing it manually. I might want to change the IR to return results. The IR module to return results instead of options. That way it's easier to do control flow for. Instead of manually having to create an anyhow error for all of the, like, oh, invalid struct ID. Since fields are now... it gets good enough to pass as you, do you think it will be a similar problem as someone having clones tends to be portrayed? Like the battle of, oh, I'm the real one. No, I'm the real one. I don't really see that being too much of a problem at the moment. I might see problems where it's like a battle between the IRL version of somebody and their digital versions. Like, oh, does the digital version of me have rights, or can I put it in the coder dungeon? I'd probably put the digital version of me in the coder dungeon. It's fine, I wiped his memory, he's happy. I'd actually probably be a little bit envious of the digital coder version of myself. Simply because I wish I could never stop coding and never have to eat or sleep, and like, that sounds so fun. Imagine anyone going a while without posting an AI video stream. Mike attempted to create an AI clone to solve that if AI was capable of it. Like you're saying, like, I mean, it would be a lot harder for my YouTube channel to be dead if I had clones of myself making videos for it. The hard part about the digital clones is you wouldn't learn what they learned. And I know a lot of people don't care about that, but I do. Yeah, see, this is where the native type, the IR type of this can't be reconstructed because it's not storing the actual type of that anymore. So I'm just going to do that. Oh, we're back to S value here. I want to fix up SSA struct and SSA enum. Did I not copy the implementation for SSA enum? Looks like I didn't. Let's do that. Go. Instead of a scrum meeting of all their AI clones sharing what they learned in the case. True, but you wouldn't really learn it. Would I understand C function call ABI after one of my clones explained it to me? No. Am I going to understand it after I'm done implementing this? Mostly. Unless it's like the Matrix, where you can just plug memories back into your head, and then I can get if I have a direct digital clone of myself, that means there's a one-to-one representation of my neurons in the cloud, meaning that we could have a device also hooked up to my neurons to synchronize my, like, whatever part of the brain learns, like reorganize the neurons so that I learn what the clones learn, and like could continuously sync all of those states. Guess it would depend on how good you yourself are at explaining something to yourself. This is true. I mean, I got into content through doing tutorials, so I don't think I would be too terrible at it. I used to tutor, and people seemed to like it, so hopefully I would be able to explain stuff to myself. But digital uplink. Care about def. Flat and internal, that works fine. Values. Cogen IR. This is true. We need this to be values. Latin types internal. We're gonna say this is just type. That's because the definition of this flattened function is different. On viewerbot. I do not need viewers. I need code. Best AI vibe coder app here. No. Start crashing out. If you want to get me to crash out, recommend vibe coding tools to me. That'll get me going. Okay. So is this basically implemented? It looks like yes. Now, in a future, it's probably a future where instead of storing all of these values separately inside of these structs, instead we have a vector and then we create these like description structs as a way to like walk those values instead of like copying them. This is fine for now. Wait a second. Is there any situation where a union could be classified Is there any point at which a union would be split across two different registers at any point? Structures and unions assume the alignment of their most strictly aligned component. Each member is aligned to the lowest available offset with the appropriate alignment. The size of the object is always a multiple of the object's alignment. That's interesting. think I do account for that though. And the reason why it is this way is so if you allocate a vector of that struct, even though like you have, why would you add empty bytes to the end of a structure? It's so that if they're all in, like packed in a list, that size makes all of the structures in that list aligned, which is very good for speed things. So you sacrifice memory, you sacrifice bytes of memory to make your program significantly faster. Might not be as good for like sending stuff over the network, for instance. In that case, you want to bit pack stuff, like packed. An array uses the same alignment as its elements, except that a local or global array has a length of at least 16 bytes. Interesting. Have to keep that in mind, except for the fact that the way I'm going to be allocating arrays is as entire pages. So they will definitely be 16 byte aligned. Their alignment will be 0. Structure and union objects can require padding to meet size and alignment constraints. The contents of any padding is undefined. Yep. What I'm most worried about is used for padding in empty structures and unions. So explicitly, empty structures and unions inherit no class. That is a by default thing. It is nice that they like explicitly say that it is used for these as well, even though if I use their algorithm, I get that result even without them saying that. Anyways, the thing that is, if the size of an object is larger than 4 8-bytes or contains unaligned fields, it has class memory. So this is for both structures and arrays. If the size of an object is larger than 4 8-bytes or contains unaligned fields, it has class memory. C++ object either has a non-trivial. This is more of a front-end problem, but like if there's like a copy constructor or destructor, you need to actually account for that. But that's like a front-end thing to do. Otherwise, it's passed by invisible reference. It is weird to me that this is in that document. Like, we're talking about assembly language stuff, and then it's like C++ copy constructor. And I'm like, no, I don't care about that. We're doing C ABI here. If the size of the aggregate exceeds a single 8-byte, each class is classified as separately. Each 8-byte gets initialized to no class. Each field is classified recursively, so always 2 fields are considered, and then this is basically just like your like figuring out the class of the entire object or entire 8-byte from all of the fields within it. The thing that this isn't describing how to do is how to deal with a union. Do you treat the union as if it has multiple fields on the same 8-byte? Like, if I have a union, and like, that means like I have like potentially hundreds of fields on the same 8-byte. thinking about it, it has to be done that way. It must be done that way. Yeah, and then if one of the classes is memory, the whole argument is passed in memory. Yeah. If one of the classes is x87, x80 up, complex x87 class, memory is used as a class. So if any of those are used, then why do they have x87 and x87 up? Like, I thought that was implicit, like, vectorization of stuff. But no, they do have the whole, like, if a structure is larger than 2 8 bytes and doesn't conform to the structure in which, like, we could vectorize it. So I guess it's just for non x87 types. Okay, I want to double check. What is x87? The 64-bit... What is it? Mantissa? What is this? The part of a logarithm that follows a decimal point. The part of the floating point number that represents the significant digits of that number that is multiplied by the base to raise the exponent to give the actual value of the number. Okay. The 64-bit mantissa of object type long double. I believe long double is larger than 64-bit. Where's its implementation defined? x86. 80-bit precision. So there's a 64-bit mantissa and a 15-bit exponent. I see. There's an entire register type for this madness. Well, the actual data uses 10 bytes. The size of often reports 12 or 16 bytes. That makes sense. Nobody wants to do an 80-bit alignment. So this is a 128-bit type, essentially. That's what I was like trying to check. So the first half, the first 8-bit bytes of this is x87. The 16-bit exponent plus 6 bytes of padding belongs to x86 up. That's what this up, like, postfix means. Is that means this, like, the thing that comes after, like, x87 up is the thing that comes after x87 classified arguments. Int 128 operate the same operations as integers, but they do not fit into one general purpose register, but require 2 registers. For classification purposes, int 128 is treated as 2 64-bit integers. Cool. With the exception that arguments of type int 128 that are stored in memory must be aligned on a 16-byte boundary. Wouldn't you just like 64-bit align them? I don't know. Arguments of type complex T, which I have no clue what that is. Is this like a oh, it's just real or imaginary, but as like a language construct? Mathematicians. I guess this is mathematicians getting into coding. I guess mathematicians invented coding, so like I want my imaginary type so I can represent quaternions properly. Okay. A variable of complex long double is classified as type complex x87. Is there a register for complex 87? x86 complex types. No. Does my CPU literally have an instruction set for imaginary numbers? Older set of instructions operate on a stack of 80-bit registers. Perform an operation, the floating point unit would perform several steps, load the real parts of the complex numbers onto the stack, perform the necessary arithmetic, store the result, and repeat the process. Okay, so even though x86 doesn't seem to be... Imagine if the writers of these papers treated them like code in IDE with various color-coded terms. I like this idea. I might do this for spec sheets that I make. And I'll probably annoy C coders, but then like anybody under the age of 30 will probably be fine with it. Of aggregate structures and arrays and union types works as follows. If the size of an object is larger than 4 bits, yeah. I'm not worried at all about these x87 hubs. No long double support. You get to deal with you can have 64-bit floating point. You cannot have 80-point floating point. I'm sorry. I'm drawing the line there. Yeah. Floating point is such a mess. Integers are mostly fine. I mean, floating point is a mess in the fact that like there's so many different representations of them, but integers are only a mess in the fact that like x86 processors didn't name them like int register 0, int register 1, int register 3. Instead, they had to name them RDI, RDX, RSI, because of course you're using each one of these int pointers or something, so we're going to name not int pointers, int registers for things. So we're going to name them. Sorry, not integer registers, general purpose registers. They can't store floating point values. So basically, I'm not going to worry about x87. I might put placeholders for them into my code, because to be honest, it won't be too hard to add in support for this later. But anyways, I think that answers my question of can a union be passed as two registers? Yes, it can. And I hate it. So, my incasting scripts have to account for the fact that class of X87 are the ones who came up with having the size of the floating point. I'm not a part of the fandom, but I understood that reference. Yeah. And we definitely have to do the casting because on return, RAX will concern the address that's been passed to the thing in RDI, so that's by if the class is memory. If the class is integer, the next available registers of the syntax RAX RDX is used. If the class is SSE, the next available register of the sequence XSM0 XMM1 is used. So basically, Linux is superior because it can return two registers. Windows is not superior because it only can return in one register. Unfortunately, this does mean that I'm going to have to deal with casting unions into two different SSE values. I love this. Alright. I do need to go to the bathroom though, so I'm gonna take a quick break. And then be right back. We are going to finish implementing our S value stuff, and then we're gonna implement incasting as a member type of S value class because we need to be able to account for nested structures, even though like incasting nested structures, like they're gonna be like not very nested. Thanks. Exactly. I might even implement something like try incast, but the problem of like trying to incast something is that you have to do something like defer writing of IR instructions, like have the ability to roll back the intermediate representation, the instructions that you've already emitted to like do stuff. But yeah. For deferring stuff or like storing like closures or something. We'd have to figure out a way to erase instructions we've already written, and I do not want to have to deal with that. In fact, because we'd be doing like branching control flow. So I don't know. I don't want to have to deal with that at all. Anyways. we're gonna have to int cast unions. Okay. The problem with from fland is at least in this case, is actually, wait a second. What's the name of this class? Crane Lift JIT backend? Do I use any self values here? I do not. We can just make this a static function. There we go. What is this complaining about? Ah. What's this? I'm not worried about this at all. This is deprecated code. You're going to be getting function signatures from the construct function signature function right here, which I think the construct function sig is at least done for Windows so far. So I'm actually going to swap out that code right now. Right here. Function signature equals not actually anything, because signature equals self construct function signature function module? Is that it? Yeah. And now here... we push to our function map, which is actually a vector, but I'm calling it a map because it's the map from integer to, yeah. We JIT the function. That fixes all of that code. Then here's the call code. All of this is completely cooked at the moment. We don't need to worry about that. But what it does mean, so... is that now inside of... well, we're not there yet. Care about cast int, or cast from int, or enum cast int, because we're doing that right now. There, no, not that yet. There it is. No, wait. Can't find it. Here it is. Crane lift, JIT backend, JIT type. There we go. Right, this wants not a tuple. Glad that I'm writing this code after rewriting this code. There we go. It felt surprisingly easy. We'll see what happens when we start actually trying to use it now. Dang it. Do I have to import my loading code too? That would suck. And the thing is, I can't really generalize it between the two systems that much. I don't know how to, like, generic this. Just a bunch of utility. Yes, it is like utility structure, but I don't know how to generic it. Ooh. I wanted to do something. I do have to write a new store operation. You're going to create a store. Also going to have a load, and the load is going to return self. And we get to learn how the stack works in Crane Lift. So what we need is function context to the current function. In the case of loading, we need IR the pointer that we are loading from, the type that we are loading, which is going to be an IR type. In the big picture, what are you working on, like, part-wise? Rendering, debugging, optimize, etc. Scripting language. We're working on the scripting language, and basically only the scripting language at the moment. Now, I'm working on the scripting language more than usual, because there's a chance that if I get it working like pretty fast here, we'll actually use it at the studio that I'm working at. Because we're considering exploring the possibility of writing our own engine as opposed to using a pre-existing one for the studio. And if we go that route, that would probably become the new thing that would eventually, some version of that would evolve into Brane Engine, and the majority of my effort would be going into writing that internal studio engine. Which maybe it's open source, maybe it isn't. That is like a discussion for the team to have. But I really want to get this scripting language working because it is the perfect solution for a vision that I have in the context of the studio, which is having a bunch of playtesters playtesting the game at once. Like, we have a big playtesting session going. Maybe it's like 20-something people. Some people are on Quests, some people are on like PCs, maybe different OSs. And what I really want is to be able to, like, somebody in this playtest comes up with an idea, we go, oh, that is an amazing idea, I want to test this up right away. And instead of having to wait till the next playtest when we've done builds for every different platform, I want to just open up the code base, change like whatever line of code it is, and then push an update to all these playtesters as the playtest is going, and then have, you know, a live reload happen on all their devices simultaneously across all these different architectures, and then just like nobody will think anything of it. It will just work. And be like, cool, we're testing this feature now. But you kind of need something that straight up doesn't exist for that to work, which is what I'm working on right now with this scripting language. Yeah. So in the language, what exactly are you constructing? Like variables, input, outputs? Right now we're working on the function calling ABI to be able to pass both structures and discriminated unions, also known as like Rust-style enums, to and from functions, because that is not something that our just-in-time compilation backend handles or library handles. And what that is when you're loading a Brane script, you're not running it in an interpreter. It's getting just-in-time compiled into machine code, and then just run directly on the CPU. Yeah, makes it a little bit harder to actually add runtime features. But it means it's going to be the fastest scripting language on the market. And I literally mean it is going to be the fastest scripting language. Like, it will be speed-wise about the same as like WebAssembly, but WebAssembly is very constricted, contained. It's hard to send memory, like large chunks of memory from one WebAssembly block to another. It's also really hard to multi-thread WebAssembly, and those are problems that I have solved. Yeah. Trying to make it do as many actions as possible in a second. I mean, technically, yeah, that's why you would go with a like JIT compiled thing instead of an interpreter. It's straight up faster. I think of it more in terms of efficiency. Like, don't do more work than you absolutely need to. Is more so the way I think about that. But essentially, yes, you are trying to do as many actions as possible in a second, including multi-threading. Did my music just run out? It's just that one song. That when the song ends, it's a really long, like, tail to it. Okay, so to load a value, we're gonna have to match on the type. For a native type, we just do context so will be context builder, instruction builder, load, IR type. So this will be crane lift JIT backend JIT type. And then native type. Since we're passing in not a Brane script pointer to this, we don't have to worry about any of our like JIT complication. any of our JIT whatever stuff. And I think for this, I might want wrapping. Trap code, heap out of bounds, simply because I might not control the caller. Trap code is configured with none though. Method will return. I'm not quite sure how heap out of bounds is. They're not out of. I reported this way. Some are detected by a segmentation fault on the heap, unmapped, or offset guard pages. I'm trying to remind myself what trusted does, because, like, you're still gonna have, like, sig 5, like, null pointer errors, right? Regardless of if you set this to trusted or not. I think. Known to be aligned and non-trapping. Is trapping a CPU level thing? Is this... Well, I'm not caring about that. Oh well. In any case, I'm going to set this as trusted. For now, just because I don't want crane lift adding anything extra into there. Then I think I put in the pointer. Yeah. Pointer and the offset. Now, technically, we could emit this with... right. Makes me want to say offset. Since this is a case where we do have compile time knowledge of what the offset is. Lens from I32. Is the implement from U32? Looks like it does. Okay. So you're gonna need... nope. It's just being slow. Offset implements from I32. I feel like this has worked with like I64 before, but I don't know. IR gets struct ID. Okay, or me how invalid struct ID. ID, and then we can error check that. Let layout equal IR or def layout, then IR. This does do a result? Yeah. And then fields is just... Oh, it is just an S value, so I can literally just do S value load here. Then in this load, we can do... So you have to pass in the pointer, base offset plus the member offset. Just to be sure, this is yes. And we have member type, IR context. And then that will individually load every single one of the struct members properly. There we go. That should work. Yes, it did. Nice. And now we just have enum. Enum. Well, we know that it starts out as this. And ends with something like this. I guess the easiest part is just getting the index and the index type. And that's part of layout. need to break this out a little bit because we do need to do a little bit of error checking. At least I think. Oh, no error checking. I could have just done a map statement there. Here is our index type. And now we need to load our variants. Well, first, if let sum. If we have an index type, that means we have types to be indexed. Index equals this. Wait, I'm gonna get a little fancy with this. So we're gonna load index type like that. Now we get to load each one of the variants. Now I think this would compile fine if I didn't do any branching and I just omitted load instructions for everything, because Brainlift still would need to potentially would have some optimization passes that would do the opposite of hoisting and lazily omit the instructions to load stuff. Into those different values, into the, like, it put it into the control flow that needed it instead of just omitting it all there and then, like, throwing everything onto the stack and overflowing it or not. I can't necessarily trust that, so I can't necessarily trust that it would actually, handle that correctly. So instead, what we're going to do is we're going to actually emit control flow. So we have this front end switch here. Which does require a default block. Fortunately. And I don't really have anything to do in that default block. Except return to the join block. So I'm just going to grab this code here. And this is going to complain a lot at first. So if this switch, we can get block. Okay, so what this was doing before was, right, since we already had blocks that existed, I'm trying to figure out if this will break absolutely everything by having control flow outside of the branches that my code is aware of. All right. Don't go. There it is. Picking on some ant poison in my room. And the ants do like the poison. A lot. A concerning amount. Which is good. Okay, so we're gonna create a new block. I don't think we're gonna need any block arguments because we don't really have block values that could be one or another necessarily. Luckily. We're going to say let branches is equal to def.variance iterator. We're going to zip this iterator with the iterator for layout. Oh, actually, we don't. Right. We don't have to deal with that. Thank goodness. Then we map this to something. Then we collect. And we probably need to error check this, but I don't know. Actually, I know that we do. Because variance, you don't have tuple types. You just have types. And we're going to actually, which means we need to filter map here. For branches. That means we can't get S values for them. Wait a second. Thinking. We're just going to do this the old-fashioned way, or v in def variance. We want to say let block Oh, I don't have to do a list of branches. Okay. Condition is literally just, here we go. Condition is index. So we're switching on the index. Nice. I don't even have to do any int casting. We're good. get away with this. Block is equal to context builder. Create block. Oh, wait. Let's say let current block equal context builder current block, like that. Then after switch emit, I assume emits on the current block that we are on. So I'm going to say context builder block, switch to block. I'm going to say previous. Just like that. Do these have results? Option. Okay. Now here we need an index, so we're going to say iterator enumerate. Set entry and do I as I-128. Then here, if we do context builder, switch to block, now we can emit instructions as if we are inside this block. And what we're going to do is say right away, I'm just going to make sure that we're going to the join block, like that, unconditionally. Block call label, block call args, no args. And that's pretty clean. And then after this, we have to remember to context builder, switch to block, join block. And if we are lucky, it will be happy about all the control flow there. And then we can say variance, or rather if let some variant type is equal to variant type is enum variant, so ID and type. So I'm actually going to put all of this into a let some vtype else continue. We have a header guard here, and we only create a block for the switch statement if our Brane, work with me here. We only create a switch for this if statement. We only create a branch of this switch statement if the enum variant actually stores data. Otherwise, it's just used as an index and we don't need to load it. There we go. Finally. So then in here we would do variants, push, and then inside of the variants push we do s value. We're reading right now, right? Loading, yes. S value load. Then we load with the same pointer, but our offset is layout union offset as I32 plus base offset. Then we just have our other filler arguments, which are the type that we're loading, which is the variable type. Actually, if I just reference this right here, as I should, makes this a reference, not need to be explicitly a reference, and then finally the IR. This last one, context. Right. Well, I accidentally made my code more efficient, but else, the else statement here we want to push none for no data in that variant. That is a lot less code than I thought it would need to be, but we do have a lot of boilerplate around it. Also, my LSP is really slowing down for some reason. I'm gonna restart real fast. Nice. So now we have a way to load values directly from memory and we're respecting the like flattened syntax we currently have. So now we just need to do the exact same thing, but storing it instead of loading it. And we use these two for when we have to pass values on the stack to stuff. But since I already wrote this switch statement code here, which is a lot easier than I was expecting, I can use the exact same switch statement code for int packing. Does it have a self-store method? No. Into the memory flags, the value to store. Pointer, value pointer offset. I want to do def members. I want to do object fields. And we want to do in case we do need to still load the index, but we also need to store the index. So we're gonna say context builder insert store the value, which is index. We don't need the type. We just store it like that, and we don't need the type. We only need the type for loads, apparently. So I can once again simplify this statement to just be if let some index. But we do still need it. Because we do still need to load it for the branching. Oh wait, we don't need to load it, because we have it already. There we go. This is all we need. Now in here, instead of variance, said we do object variance. Okay. So we have both load and store from memory written for both load and store. Amazing. Now we just need int casting, or registered casting, I guess. Arg casting? I don't know. Yes. I guess what I need is this exact same code, but instead of inserting a store, instead it's inserting a bit shift, or a bit cast, a bit shift. It's a series of instructions to be. First, it is a First it is a bit cast, and then an unsigned extend if needed, and then it is a bit and operation with the last value, if there is a last value. For that index. Okay. I'm going to be right back, and then we are going to write that actual bit casting and reading code. Alright, so we have load, store. See, the thing is, I guess I don't have to account for vector registers ever. So we should be safe. We should be safe to int cast. As we normally would, since vector registers are... No, because we could have a case where... Yeah, we could have a case where half of a structure is cast to an int and the other half is cast to a vector. This is almost making me want to... Hmm. Oh man, my brain's rebelling. Hoping so hard. Or refusing to write the code so hard that we're just straight up not coding. Okay, so the problem is... that over here, structures are basically always turned into 2 registers. Okay. Okay. I don't have to deal with vector registers. This is good. This is good. Okay. If the size of the aggregate exceeds to 8 bytes, of course, and the first 8-byte isn't SSE, or any other 8-byte isn't SSE up, the whole argument is passed in memory. So this means specifically that one 8-byte, if one 8-byte is something else, like a float or an int or whatever, is either a float, a bitcast float and int, or just like whatever's going on over there. If one argument is that, and the other is SSE, which is like a float, and then a bunch of other floats that could be vectorized into a single register, and then have those two passed as a 2-register thing, it doesn't do any of that. I was overcomplicating it. It's just if the entire struct can be turned into a vector register, they do, but they don't turn a second 8-bit argument into a vector register. No. It's can the entire thing be a vector register? Convert it. Otherwise, don't. Oh, these clones would be so great right now. The clones would act exactly the same. But this is good because this means that I can write my casting code as long as the Arch version isn't like insane, like something out of like a madman's dreams, which I've heard from my other friends who has done assembly stuff that apparently they thought this one in particular was crazy, which I'm like, have you seen this one? Anyways. We can work with this. I can work with this. I can make one casting function that will work for both Windows and Linux, and it will support casting a type to multiple 8 bytes. But I'll be able to, before calling it, limit the number, limit the size, because I also need to account for these other things. Once we account for these other things, then we'll incast it, because we decide to incast it after classifying the way to pass a struct. So here, yeah. If the class is memory, if the class is integer, if the class is SSE, the next available register is used. The registers are taken up. If the class is SSE up, the 8-byte is passed in the next available 8-byte chunk of the last used vector register. SSE up is not preceded by SSE or SSE up, it is converted to SSE. I might not need to do the vectorization myself either, because it looks like the vectorization is not done on the structure level. The vectorization is done on the argument level. See, if the class SSE up, if the class is SSE up, the 8-byte is passed in the next available 8-byte chunk of the last used vector register. So that is doing the vectorization after after all the argument types have been determined, meaning I don't need to do the vectorization. This is if SSE up is not preceded by SSE or SSE up, it is converted to SSE. Which confuses me. If the class is SSE, then the next available register is used. XMM0. XMM registers are 128-bit registers used in Intel's streaming SSE for parallel processing of floats and a floating point and integer data. The point of the x86 instruction set and are accessed through SSE instructions. There are 16 XMM registers. So, if the class is SSE, that means that SSE ups are passed in the next available 8-byte chunk of the last used vector register, which these are vector registers. So what this is saying is group this float in with the last float passed. That's what that's saying. Yeah, so I don't need to do this manually, because guess who's in charge of doing this? CraneLift is in charge of doing this. So all I need to do is give it integer or floating point arguments, or it would even take care of x87 arguments. So if I ever support those, it would take care of those too. I don't need to worry about it. I don't need to worry about it. We're good. XMM are floating point arguments are passed in XMM. Can you pass vectors? I guess I don't need to worry about it. Ah, here we go. I never passed by immediate value. Instead, a pointer is passed to memory allocated by the caller. Yeah, we're gonna use SIMD types, but they're going to be slow. You can't pass SIMD types as... Lynn. On reference? No. When did the first AMD 64 spec come out? First AMD 64 specification was released in 2000 with the first processor, the AMD Optron, shipping April 2003. For some reason I feel like that, like, x86 has been around. So I've been around longer than x86? Well, not x86, but x86-64 specifically. The documentation has been around longer than I have, but not since the implementation. Really? SIMD was a part of the OG spec. Okay. For some reason, I feel like SIMD would have been invented after 32-bit. Or 64-bit. Because 32-bit processors don't give me SIMD vibes. Oh, but they do support returning vector types. I see. That's really funny to me. Oh yeah, you can't pass vector arguments to functions, even though there's vector registers. But you can return vector registers. Alright. So I'm just going to copy both of these. You know what? Screw it. We are going to initialize with zeroed out values and then and them after the fact. Arbing? What if the optimizer can handle it? I don't know. Can't get myself to do it. I'm gonna have to do the more implemented way. See. So we're gonna store, well, not store, but we're gonna, this is where we're gonna do value is equal to context builder. Let's pseudocode this out. So this little bit here is really the only place that we're gonna write stuff, and even down here in the enum for the index, for the index I'm gonna cast it to an s value, and then still use this code up here. So when we are writing this to one of the vector arguments, I'm gonna say if arg's length is less than start arg, less than or equal to start arg, arg's push value that gives us that new index to work with there. And we shouldn't do anything else. We have given the argument. Technically. Oh no. Actually, it's fine. I can deal with this. I was thinking about in the case of the enum, when we load values, we're literally gonna have to do like block arbs and all of that nonsense. Actually, do we? Yeah, we have to do block arg nonsense for storing. We don't have to do it for loading. Wait a second, how does this... Does this handle 2 floats? One of the classes is memory, the result is the memory class. If one of them is integer, the result is integer. If one of the classes is x87, complex x87 memory is used as a class. Otherwise, class SSE is used. Class is SSE, the next available register is used. Either non-trill. The size of an aggregate exceeds a single 8-byte. Each is classified separately. Each 8-byte gets initialized to class, no class. Each field of an object is classified recursively, so always at least 2 fields are considered. The resulting class is calculated according to the classes of fields in the 8-byte. If both classes are equal, this is the resulting class. If one of the classes is no class, the resulting class is the other class. If one of the classes is memory, then the result is the memory class. If one of the classes is integer, the result is integer. So this is easy. That's if you have a SSE registered thing and an integer registered thing, you just classify the entire thing as integer and cast the floating points to integer. If it's any of these 80-byte things, you just pass pointer, otherwise class SSE is used. What I'm trying to figure out is if I have 2 32-bit pointers in if I have two floating point numbers, the 32-bit ints, they're going to be contained in the same 8-byte. And they will both be classified as class SSE. I'm not aware of a way to pack two floats into a single float value, aside from it just being an XMM register that's a vector register. Like, often there would be scripting where a component... Scripting would be a component often for props or interactables. A lot of times those groups, like, fully, like, utilize the roleplay aspect, because if they're role-playing, you don't need to script stuff. It's like D&D. A lot of D&D stuff. It's nicer without scripting stuff, but a lot of times, I guess it really depends on the group. Like, I've tried to code stuff for a D&D group before, but then you realize, like, it doesn't really make sense to you most of the time. The bandwidth of content for that sort of scenario is much higher than your capacity to make stuff for it. If the class is SSE, the next available register is used. When value of type bool is returned, it shall be passed in a register on the stack. Returned or passed in a register on the stack. 0-bit contains the truth value, and bits 1 through 7 shall contain 0. Yep. If there are no registers available for any 8-byte of an argument, the whole argument is passed on the stack. If registers have already been assigned for some 8 bytes of such an argument, the assignment gets reverted. Interesting. Actually, that's scary. If there are no registers available for any 8-byte of an argument, the whole argument is passed on the stack. If registers have already been assigned for some 8 bytes of such an argument, the assignments get reverted. That means if I have a struct, I'm trying to pass this struct, and it falls right on the boundary between one of its bytes being in a register and one of its 8 bytes not being on a register. The whole argument is passed on the stack. Now, see here, I don't know An XMM register can hold 4 32-bit single precision floating point numbers, which are the SSE values. For some reason I thought it would be more. So out of 8 bytes of memory, into 56 are split into 4 8-byte chunks. The least significant one belongs to class SSE, and all the others belong to SSE up. To me, that implies that all of them fit into an XMM register. Wait, 8-byte. 8-bit or 8-byte? No, that's 8-byte. 8 bytes is the size of 64-bit. Because 8-byte. 64 means 232-bit. The class is SSE. Nope. Wish they'd be more specific about arguments of type float double, decimal 132, decimal 164, and M64 are in class SSE. Class SSE is a vector register. I'm very tempted just to write different functions for... Yeah. Post-merger cleanup is done if one of the classes is memory. So these are just for the... These are just for the struct, not over every single argument. Meaning that this operation of merging SSE values doesn't happen to every single argument. Meaning that I do need to be careful about crane lift. Crane lift's abstraction over the calling conventions, because if the class is SSE, the next available vector register is used. So if something isn't classified SSE up, then it doesn't get put in a vector register. Meaning that if I want to vectorize stuff, I have to do it manually. And it only auto-vectorizes structures, and it doesn't auto-vectorize regular arguments. So I guess SSC is specifically... This takes up all of the lower bytes of a vector register. This takes up all of the higher bytes of a vector register. Or can. Exceeds 2 8 bytes, and the first 8 byte is an SSE, and any other 8 byte is an SSE up. Next available 8-byte chunk of the last used vector register. How many 8-byte chunks are available in XMM? XMM register is 128 bits. So that's 2. So SSE up. Two 64-bit floating points. $32-bit is 4-byte, not 8-byte. I think YMM registers are... XMM registers are 128-bit longs and represent the lower 128 bits of the YMM registers. The YMM and XMM registers are overlapping. So a YMM register could contain for 64-bit floats. Used to pass floating point arguments. XMM. Okay. The AMD 64 architecture provides 16 general-purpose 64-bit registers. In addition, the architecture provides 16 SSE registers, each 128-bit bits wide, and 7 floating point registers, each 80 bits wide. Each of the x87 floating point registers may be referred to in MMX 3D Now mode as a 64-bit register. All these registers are global to all procedures active for a given thread. Intel AVX Advanced Vector Extensions provide 16 256-bit wide AVX registers, YMM 0 through YMM 15. The lower 128 bits of YMM 0 to YMM 15 are aliased to respective 128-bit SSE registers. For the purposes of parameter passing and function return, XMMN and YMMN refer to the same register. Only one of them can be used at the same time. We use vector register to refer to either SSE or AVX register. This subsection discusses the usage of each registers RBP, RBX, and R. Okay, so I guess this section here basically says, even though they're saying XMM, that can just mean YMM. And yeah, even though they explicitly say XMM, they also explicitly say that XMM actually means YMM, so yeah. Last used vector register. XMM is a vector register that could mean YMM. So yes, we can in fact fit 256 bits of float in a single register. Meaning that if we classify 8 bytes as SSE, and then 3 other 8 bytes as SSE, you can in fact just vectorize the entire structure. Oh my. Which means we do have to vectorize structures ourselves if they are vectorizable. If they are not vectorizable, we do pack 2 floats in an XMM register. Okay. How do we make this work? How do we get this to work for both System 5 as well as Windows? Well, what's the difference between the two when it's only a single 8-byte? If it's only a single 8-byte, then that would filter out every situation except for packing 2 floats into the same float vector register. Whereas on Windows, all aggregate types are bitcast to ints. Integer valued arguments in the leftmost positions are passed in left to right order. The 5th and higher arguments are passed on the stack. All integer arguments registers are fine. Structs or unions of other sizes. Oh, here we go. In 28 types, arrays and strings are never passed by immediate value. Instead, a pointer is passed to memory allocated by the color. Structs and unions of sizes 8 to 64 bits and M64 types are passed as if they were integers of the same size. So even if you have multiple floats, in the same bit of memory, you still do need to pass them as cast to an int. Okay. I think with all the little tiny differences between all of this, I think that the only thing I write a utility function for is yeah, the only thing I write a utility function for here is for casting values to integers, and really that's it. Casting things to integers with a helper, And then I'll just throw that into our function call code right next to in the Windows ABI and also in the System 5 function calls in there just to be sure. And then for this procedure call standard, aggregate. The alignment of the aggregate shall be the alignment of its most aligned member. The size of an aggregate shall be the smallest multiple of its alignment that is sufficient to hold all of its members. Okay, so that's the same exact thing the other document specified it as. Let's see. Subroutine calls? Yeah, subroutine calls. Parameter passing. The base standard provides for passing arguments in general purpose registers R0 through R7, SIMD floating point registers 0 through 7, and on the stack for subroutines that take a small number of small parameters, only registers are used. And I don't care about Vardex subroutines. Parameter passing rules. Parameter passing is defined as a two-level conceptual model. A mapping from the type of a source language argument onto a machine type. The marshalling of machine types to produce the final parameter list. The mapping from a source language type onto a machine language type is specific for each language and described separately. The C and C++ language bindings are described in this section. This is how we map arithmetic types. This is how we map pointer types and enumerator types. For enumerated word, int or unsigned int. For all enumeration types, the container type shall be unsigned int, unless that is unable to represent all the declared values in the enumerated type. If the set of values in the enumerated type cannot be represented using either int or unsigned int as a container type, the language permits extended enumeration sets, then a long, or unsigned long type container may be used. All values in the enumeration are inside in the range of unsigned long within the container type. Unsigned long, there is a container type this long. I don't know what enumerated types are. Is that discriminated unions? Like, what are we talking about here? Additional types, size T. C and C++ require the system to provide additional type definitions. Yeah. Here we go. Structures and unions are laid out according to the fundamental data types of which they are composed. All members are laid out in declaration order. Additional rules applying to C++ non-POD, whatever that means, are described in C++ ABI 64. I don't care about C++. We are doing C. It feels... Argument passing conventions. Okay, so they have a separate section in this document for the argument passing conventions for structures. The argument list for a subroutine call is formed by taking the user arguments in the order which they are specified. Cool. The argument list is then processed according to the standard rules for procedure calls. Or the appropriate variant. This is still the procedure call standard. The ARch64 architecture supports a number of short vector operations to facilitate accessing these types from C and C++. A number of extended types need to be added to the language, following the conventions used for adding types. Yeah. C++ mangling. I guess this is still in, it says here that we're still in the procedure call standard, so I guess all of this still falls underneath it. I'm going to search struct since they seem to use that term. So that's the layout. Floating point and short vector types are passed in SIMD and floating point registers or on the stack. Never in general purpose registers, except when they form a small structure that is neither an HFA nor an HVA. Okay, here we go. If the argument type is a composite type whose size cannot be statically determined, if the argument type is a composite type that is larger than 16 bytes, then the argument is copied to memory allocated by the caller, and the argument is replaced by a pointer to the copy. So, if the argument type is a composite type larger than 16 bytes, so I think composite type refers to structure. Which they will explicitly say somewhere. Composite type. A composite type is a collection of one or more fundamental data types that are handled as a single entity at the procedure call level. A composite type can be any of an aggregate where members are laid out sequentially in memory with inter-member padding, a union where each of the members have the same address, and an array, which is in a repeated sequence of other data types. The definitions are recursive, that is, each of the types may contain a composite type as a member. Yeah. Why didn't this show up in the search? COMPOSITE. Yeah, it just doesn't show up here. If the argument is a composite type, then the size of the argument is rounded up to the nearest multiple of 8 bytes. Okay. The argument type is a composite type that is larger than 16 bytes. Then the argument is copied to memory allocated by the caller, and the argument is replaced by a pointer to the copy. So 16 bytes is the largest structure we can pass, which isn't a lot to work with. Okay. If the argument is a composite type and the size in double words of the argument is not more than 8 minus NGRN, and NGRN is the next general purpose register number, and the size in double words, I believe that's 16 bytes, then 8 minus NGRN. Then the argument is copied into consecutive general purpose registers. Starting at X NGRN, the argument is passed through as though it had been loaded into registers from a double word aligned address with an appropriate sequence of LDR instructions loading consecutive registers from memory. The argument is a composite type and the size in double words. ARM 64D word size. I'm just double checking. D word is 64 bits. Okay, I was completely wrong. Word is 16-bit. No. Byte. Double byte. I've coded in assembly language before. I should understand this. Anyways, double word is 64 bits. I was completely wrong there. The size in double words of the argument is not more than 8 minus NGRN. So it looks like the Windows calling convention of just bit casting structures into integers is the standard, and x86 Linux is the madness. So if you have a way to bitcast ranges of structures, then that's all we need, is to be able to bitcast memory ranges of structures to ints. Your N is set to 8. The NSAA is rounded up to the larger of 8, or the natural alignment of the argument's type. If the argument is a composite type, then the argument is copied to memory at the adjusted NSAA. The argument has now been allocated. For each argument in the list, following rules are applied in turn until the argument has been allocated. Okay. So the statement "the argument has now been allocated" means stop going down the list of instructions. This is essentially pseudocode here. So if the argument has not been allocated, then you allocate the argument on the stack. The size of the argument is less than 8 bytes. Then the size of the argument is set to 8 bytes. The effect is as if the argument is copied to the least significant bits of a 64-bit register, the remaining bits filled with unspecified values. The argument is copied at the adjusted next stack. The next stack argument address. The next stack argument address is incremented by the size of the argument. The argument has now been allocated. I guess this is like the thing to do in the case of like if arguments haven't been used up or something. Hello. Wait, oh, I read this completely wrong. This is not 16 bits. It's 16 bytes. Okay. It's 16 bytes, and the argument is alignment of 16. If the NGRN, next general register number, is rounded up to the next even number. That's weird. That sounds like it would skip it. General registers. So for this, I might need to write my own. For this and this, I might need to write the calling convention code from scratch, just because I need to know how many general purpose registers are left. Because if we can't fully allocate a structure, on Brane, work with me here. Yeah, if we can't fully allocate the structure on the stack, it doesn't. It straight up doesn't. It passes it on the stack. In fact, it passes all arguments from that point ordered on the stack. Because the instant you fail to allocate anything in registers, immediately it switches to stack values. So if you threw a massive structure as the first argument of a function, like if you put a massive function as the first argument, suddenly our massive structure by value as your first argument, suddenly nothing on this function gets passed by value. That explodes. And wait. What? I don't know. What are we making? Right now, we're working on a JIT compiled scripting language for the game engine I'm making. But right now, what we're trying to do specifically is make our JIT compiled functions conform to the C ABI for all of our target platforms, which are Windows x86 64, Linux x86 64, and Arch 64. And unfortunately, they all have very different opinions, and it's kind of hard to reconcile all of them, especially because the JIT compilation framework here kind of takes care of function arguments for you, but it doesn't take care of anything but register values for you. So if you want to do structures, you have to do that yourself. And the problem I'm running into is Windows is fine. They have an extremely simple calling convention, so I'd be able to implement this no problem if it was the only thing I was implementing. Problem is System 5, the calling convention used on both Linux and ARM, Linux x86 64 and ARM Arch 64. Both of those have a thing where a structure can be split up across multiple function register arguments, But it seems like in both cases where, yeah, if there are no registers available for any 8 byte of an argument, the whole argument is passed on the stack. And in here, the NGRN is set to 8. This description of, well, actually, no, here. If the argument is a composite type, size in double words of the argument is not more than 8 minus the NGRN, or next to general register number, then the argument is copied into consecutive general purpose registers. So what this is saying is basically, if you don't have enough general purpose registers to put this structure into general purpose registers, then instead move on to this behavior here, which is, if the argument is a composite type, then the argument is copied into memory at the adjusted next stack allocation. Yeah. Yeah, this is assembly code stuff, and yeah, procedure calls. They're not even calling them functions, they're calling them procedure calls. So basically what those two lines are saying is, when I'm trying to wrap my JIT compilation library's behavior for passing structures, what that's saying is that I need to know the current number of, in the case of x86 system 5 or x86-64 system 5 function calls, or system V function calls, I need to know the number of available integer and SSE registers, so general purpose and vector registers available, before deciding if my structure goes on the stack or on the heap. And in the case of ARM64, I need to know if it is, well, just only general registers, because it only does general registers. So what I really need to know is, there's these argument purposes, and you can say that this is a struct argument. My understanding is that struct argument is specifically talking about when we have a structure that we need to pass on the heap. That's my understanding of what struct argument means. But I wonder if struct argument also takes into account all these different calling convention things. It wouldn't be able to take into account System 5's on x86-64's split from vector registers into it wouldn't be able to account for the whole 8-byte encoding scheme if it's split across two, because there could be one float argument and one integer argument. Like, with the information it has, it would not be able to do that. It wouldn't be able to. But I do want to look at Is it possible for me to see a switch in... Brain lift, function calling, convention. Oh, Windows ARM still uses Windows Fast Call. Libcall, interesting. I guess library calls are different. Maybe. But these are the only options. So I guess it would still be Windows Fast Call or System 5. Okay, that's fine. We have crane lift here. I want to search in crane lift for what's crane lift reader? This create library supports reading CLIF files. Functionality is needed for testing crane lift, but not essential for a JIT compiler. So for some reason they have struct argument. That's hard. But I don't know what it does. Language Interface Foundation is a tool that helps create Python bindings for C++ code. Interesting. So it uses struct arguments. Just wherever. This is the x86 ABI. Struct argument parameters are not supported on ARM64. Wait. Repadding an extension of arguments if the argument is type composite type. Is a composite type that is larger than 16 bytes, then the argument is copied to memory allocated by the caller. The argument is replaced by a pointer to the copy. So yeah. If the argument is a composite type, then the size of the argument is rounded up to the nearest multiple of 8 bytes. Okay, so they're doing like the whole 8-byte thing. The argument has now been allocated. .64 ABI RS. The struct argument would be able to be implemented for ARch64. I guess x86 is the only architecture that you really use it on. Any param uses extension, winch calling convention. The winch convention will not pack its results on the stack. Instead, align them to ABI boundaries. Is this winch? Local args. x86 ABI machine spec. Parameters are always either passed in 2 registers or on the stack, so handle that as a special case. The loop below. Okay, so they handle all the calling conventions in one giant function. And we also need to consider... So we need to... I don't want to rewrite function calling conventions from scratch. So instead, what we need to do is... have some way to split all arguments of a function into some system. Alright, I need to think about this more. I'm not going to get much further. I've actually read all the calling conventions. I need to sit and think for a little bit. So I'm going to go eat some food and hopefully have an epiphany that makes it easier to deal with all of this. I'm not sure that I will have that epiphany though, because yeah. Alright, I will see you around.